finished off last time. This is where we were. So let's finish this problem. Let's review what we were doing. We had this function, this multivariable function. Okay, we had this multivariable function, 3x squared y plus y cubed minus 3x squared minus 3x squared plus 2. And we said we wanted to identify all the critical points. Critical points are where both partial derivatives are 0. And those would give us local maximums, local minimums, and saddle points. Okay, so what we did, we took the first partial with respect to x, and we got 6x times y minus 1, set it equal to 0. And then we took the partial with respect to y, and we got 3y times y minus 2. Or no, sorry, we got this 3x squared plus 3y squared minus 6y equals to 0. So we're trying to figure out ordered pairs, so ordered pairs x and y that make both of them 0. Right? Ordered pairs x and y that make both 0. So we started with fx, and I said, what could make fx 0? Well, there's only two possibilities, x equals 0 or y equals 1. So when x equals 0, we'll put x equals 0 in here and figure out what y's do I need to make this one 0. And that was 0 or 2. And then to get fx to be 0, the other way was y equals 1. So I put y equals 1 into this, and I figured out what x's I need to make it 0, and that was plus or minus 1. So that gave me these 4 critical points. And then we set up a table to figure out what the discriminant was for each of the 4 critical points. Remember, the discriminant is this value that tells us what kind of critical point we have, or it helps us determine that. Okay, so quickly here, so I'll take over here in blue. So what is fxx? fxx is 6y minus 6. fyy is 6y, also 6y minus 6. Is that right? Check my math. And then fxy would be this one with respect to y. So that would be just 6x. Agree with that? Y minus 6, yes. 6y minus 6, yes. And I think that's right. So now, at the point 0, 0, what is fxx? At the point 0, 0, fxx. We only need y for that, and we get minus 6. So check my math. And then at 0, 0, fyy is also minus 6. fxy is 0. The discriminant. Positive 36. Is that right? And so remember what d greater than 0 means. So d greater than 0 means either max or min, right? It means either max or min. So how do we know what we have? We have to look at the second derivatives, right? If the rate of change is decreasing at a local max or min, which does it have to be? Remember, so if the rate is getting more negative, getting less positive or more negative, and we're concave down, right? We're concave down, so we have to have a max. So when you get the discriminant's greater than 0, you also have to check the second derivative, right? So that's here. So there, and that confirms the picture because that's at 0, 0, right? That's x, y, 0, 0, we have a max. Okay, 0, 2. fxx is, it's 0, 2. Looks like positive 6, is that right? fyy is also positive 6. fxy is 0. So 36 again. It's greater than 0, max or min. Now we look at the second derivatives. Our rate, if we have a positive second derivative, that means our rate is getting what? Less negative or more positive. The rate of change is getting less negative or more positive, which would be min. And that confirms the picture, 0, 2. Right there is our min. There's our local max. Okay, finally 1, 1, the point 1, 1. So what is fxx? It's like 0. Fyy, also 0. Fxy. Fxy is 6, so what is our discriminant? Negative 36, which tells us it's less than 0. Remember what that tells us? Saddle, and we're done. Right? We're done with that. And so I can't turn this, but remember there were 2 saddles. So there's one out here in the first quadrant and one out here in the second. So saddle there, and then we get kind of the same thing for negative 1, 1. Again, we get 0, 0, negative 6, but we still get negative 36 when we do the discriminant. Saddle. And the picture, you know, the image that I showed you of that surface agrees with that conclusion. Questions on this?
Why don't you look at Fyy when you're deciding where it's
I did. So they're both negative. Fxx and Fyy were negative. Right. So no matter which direction you go, your rate of change is decreasing.
So let's say that one's negative, one's positive.
That's in. Then if one's negative and one's positive, then it would have to be a saddle point automatically. You're going to get a negative discriminant if one's positive and one's negative. Because in one direction you're going like this, and the other direction you're going like this. That has to be a saddle point. Other questions? Yeah.
So the discriminant
the
equation is like the fxx times fyy minus fxy squared.
Right.
And is that the only form of that equation?
Well, it's really fxy times fyx, but fxy and fyx are the same.
They'll always be the same?
Yeah, that's Clairaut's theorem.
And then,
we didn't talk about that, but
fxx and fyy will not always be the same?
Oh yeah, definitely. They just happen to be in this one. Okay. Those do not have to be the same at all. Other questions? Okay. So let's keep looking at that example. I want to add a new part to it. So what I want to do now is I want to say, let's suppose our domain is restricted to only xy values such that within the region y equals 2x, x equals 2, and y equals 0. And so I want to say I only care about, so to say this is some real world problem where it only makes sense to talk about when the independent, our ordered pair of x and y is in this region or on the boundary of this region. So let's show that visually here. All right, so that's kind of a mess. But if we look down on this now, maybe this will turn this way. So now I only care about what's going on within y equals 2x, x equals 2, and y equals 0. Oh, stop. Something like that. Okay? So now I'm looking down on the z-axis, and I only care about this surface in there. And now what I want to say is I want to find what's the absolute maximum and the absolute minimum of this function, of the gold function, in that region, right? So we're talking about absolute max and absolute min. And so you have to think back to Calc 1. We're going to apply all those same principles, absolute max and min. Okay, so this means, basically, if you remember from those, we have to what? We have to check the boundary. It's the same way we did in Calc 1. We're going to check the boundary, and we're going to check the critical points. But are we going to check all critical points? So we only care about the critical points now that are inside of this region now. So if we found critical points before that fall outside of that, we don't care because we're restricting our domain to this region, combinations of x and y that fall in that triangle. Okay? So which critical points then matter? So what were our critical points? We had 0, 0, 0, 2, 1, 1, and negative 1, 1. So do all of those fall in the region? What about 0, 0? We're going to consider that? Definitely, right? That's right there at that corner. That's good. 0, 2. What about 0, 2? No, right? 0, 2 was what was that? That was our minimum. That doesn't matter because it's outside the boundary. So we can cross that out. 1, 1. Yes, 1, 1 is right here. What was 1, 1? That was one of our saddles. But as a critical point, it's important. Negative 1, 1, no. Okay, so we're going to check the boundary. But now the boundary, what consists of 3 segments. So we have to go all the way around the boundary. We're going to have to check along y equals 0, x equals 2, and y equals 2x. And each one of those problems will be like a Calc 1 problem, where we're checking the endpoints and along the middle, okay? So we're going to do each of those, and then we're going to check the critical points. And for so we're going to get a list of possibilities, and we're going to find all the z-values, right? So we're going to find all the z-values, and the very greatest z-value will be our absolute maximum, and our very least z-value will be our absolute minimum. Okay, so here we go. Let's do the boundary. The first part of the boundary is y equals 0. So for y equals 0, what are we going to do? We're going to take our function, our multivariable function, gold, and we're going to restrict it to y equals 0. So what do we get for y equals 0? We're going to get z equals what? Minus 3x squared plus 2. So should we write that out again? Let's write it out again up here. Fxy equals 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. So when y equals 0, that function just becomes along there. It's like we put that plane there. We get a trace, right? We get a trace. And that's going to be z equals minus 3x squared plus 2. Is that a thunderstorm warning or something? Oh, it's the test. Okay. All right. So z equals minus 3x squared plus 2 is going to be the trace along that surface at y equals 0. And so this is like a mini optimization problem. We got to look at the endpoints and any critical points along there. So how do we get any critical points along there? We're going to have to take the derivative. So we'll take z prime equals minus 6x. We want to know, where does that equal 0? X equals 0, which we already have, right? So we already have that point, 0, 0. So that gives us a candidate 0, 0. But we already had that one from here, but it's just a repeat. That's fine. Next boundary, x equals 2. So we're going to do x equals 2. And so we're going to find what's the trace of that surface. So this is a little deceiving, but this surface goes out. It's defined for all values x and y, even though it's not showing up there. So maybe if I zoom out once, will that help? Yeah. So you see that it's only showing part of the surface, but that gold surface is defined for all x and y ordered pairs, right? The domain is all real. The whole xy plane is the domain. So even though you don't see it in there, it's still extending everywhere, okay? So now x equals 2 is going to be the function that we get when x equals 2. What is that? So we get z equals 12y plus y cubed minus 12 minus 3y squared plus 2. And now we got a little optimization problem along that boundary, right? So we have the trace of the surface, the gold surface, along y equals x equals 2, and so we want to do the derivative. So dz dy, right? Z prime. So this was dz dx. This is dz dy. It's going to be 12 plus 3y squared minus 6y. And we got to figure out for what y values is that 0. We want to get critical points. It's like a little sub-problem, right? We want the critical points along that boundary. So that we can reduce that to, we can factor out 3. Y squared minus 2y plus 4 equals 0. B squared minus 4ac. So I think this doesn't have any zeros, right? That if you do the quadratic formula, you get a negative under the square root. So that doesn't have any zeros. There's only imaginary, no real zeros. You do b squared minus 4ac, minus 4ac. Wait a second. 0. Does it? Oh no, minus 4ac. No, that doesn't have any real zeros. Okay, so there's no real zeros. So the only thing we get from the x equals 2 boundary is, again, we would have the point 2, 0 and the point 2, 4. We're going to check those for sure. So 2, 0 and 2, 4. Endpoints, right? Endpoints of that. But there's no critical points along that boundary because there's no real zeros of that little quadratic there. All right, finally, last part of the boundary is y equals 2x. we're going to put that in. Z equals 3x squared times 2x plus 8x cubed, right? Minus 3x squared minus 3 times 12x squared. Check my math. Plus 2. Did I do it right? So what do we got? So I've got 6x cubed plus 8x cubed. Is that 14x cubed? And 12x squared minus 3x squared is plus 9x squared. No x's, plus 2. Six x cubed, yeah, probably plus 8x cubed minus 3x squared minus 12x squared. So that's minus, is this minus 15x squared?
Yep.
I missed my minus there. So take the derivative. So then we dz dx. 42x squared minus 30x. So we can factor out 6. 6x times 7x minus 5. Check my math. So x is 0 or 5/7. So x equals 0, again, is this point. We already had it, right? 0, so again, 0, 0, repeat. But this is a new one now. 5/7 is something short of 1. So there is some critical point along that boundary where x is 5/7 and y is 2 times that, 10/7. So I got this critical point 5/7, 10/7. So I'm gathering up my candidates, right? Candidates for absolute maxes and mins. I didn't get any critical points along there, so I just have the endpoints. Also, no critical points along there, so I just have the endpoints. And then for this last part, y equals 2x, I got this critical point 5/7, 10/7 right there. And we also have the critical point from the multivariable function, which was what? 1, 1. So we have to test all those, right? So I'm going to have to test 1, 2, 3, 4. Those 5 points are the possibilities for they're all the possibilities for an absolute max or absolute min on this region. So then we go to our function. Yeah.
Where's the 2024 going from the bottom? There it is.
2, 0, and 2, 4.
Right, but why are those points?
Because so like you got to think of these each of these boundaries as its own little optimization problem. And what do? You have to check the endpoints and the critical points in the middle.
Even though it's not on the function.
No, the function extends. That I was saying before. That gold function extends. Its domain is all real, the whole plane, even though it's not being shown in this image. This image is cutting it off. But that gold image, that gold surface extends in all directions. Yeah, so that was a little confusing. Okay, so then we can go to the function. Do I have that as a function somewhere? I do not. So I'll just do a new. Oh, bring me back. I don't know where it went. It's somewhere. I can get it. I just don't know how. All right, so new on the wrong file. All right, so f, x, y equals all this. So what were my candidates here? So I want 0, 0. 5/7. Okay, so I'm doing a lot of talking. Does anybody have a question? Please.
So we had previously found the critical points of the entire thing.
Right.
Now we're finding the critical points in this region. Wouldn't the critical points of the whole thing, always, like the maximum, always be higher and lower than just the critical points in this region?
But so we only care about what's in this region, right? So let's like we have like we.
If we have a point in this region that's also in the whole structure, wouldn't the one that's also in the whole structure always be higher and lower than the one that's in this region?
No, not necessarily, because we just found local max and mins, which is just the highest in the local area. So then it could be like a local max or min, and then as we get out to the boundary, it could be on its way up where the boundary is. It could be higher. You see that? So these are just local, like in a local area, and like a small disk around the point, you get a local max or local min. Move to the boundary, you could have function values much higher than that. Yeah. All right, what else? So is that 5? All right, so these are our possible candidates we got from our critical points doing the original problem, and then we got all the critical points on the boundary, right? So we got 0, 0, 5/7, 10/7, 1, 1, 2, 0, and 2, 4. So the absolute max is what? Can you read that in the back? It's the absolute max? The absolute max is not 2, 4. So the absolute max is z equals what is it? Okay, absolute max is 54. And where does it occur? At x equals 2, y equals 4. You get a maximum of z equals 54. Absolute minimum? -10, which occurs at x equals 2, y equals 0. Any questions on that? So what you'll have is you'll have some multivariable function that's like a real-world function, right? And then there'll be some set of constraints which will constrain your x and y points in the xy plane, like what we did. You know, so maybe only within the unit circle or something, right? So then you're gonna find your critical points of your multivariable function, and only consider ones that lie, say, inside the unit circle. But then you'd have to check the boundary. So then you have to check for any critical points on the boundary, like we did. We had to break it up into 3 segments. And then those critical points on the boundary plus the critical points lying inside of the region of the domain of your situation are all the fair game candidates. So you're going to find all those z values. And the biggest one is going to be your greatest value of z and its location at the ordered pair x and y. And then the smallest of all your candidates, z value, is going to be your absolute min, and then the location at your ordered pair XY. Any questions on that? Okay, so we're done.